Now we get a chance to take some of those theorems that we just learned about and use them in proofs. And here's the first one. Here we're seeing that we've got a diagram with a whole bunch of angles. And again, the first thing you should do is just kind of study that diagram so you know what's going on here. Looks like we've got two perpendicular lines, but it doesn't really show that, which would mean that hopefully 3 and 4 together are going to add up to 90 degrees over there. These two are labeled as angles 1 and 2. Over here we got angle 3 and 4. Okay, so let's take a look at now what's written about that stuff. It says in this diagram 1 and 2 are congruent, and yep, we see that. That's shown with the little arcs. We're trying to prove that 3 and 4 are complementary. Okay, so this is going to be a fairly quick solution. Angle 1 and angle 2 are congruent. That is simply because it is given to us. We know that that's always going to be the first thing that we write is what we have given to us, something to work with. The second thing that we could say about this comes from Theorem 3.8. Well, let's take a look at review Theorem 3.8 again. Theorem 3.8 is this one. Oh, come on. It says if two lines intersect to form a linear pair, they're forming a line, and then those two angles are congruent. Those angles must be right angles, making them perpendicular. Okay, so going back to what we had written here, where do I see that linear pair with angles that are congruent? From here to here. That's where we've got a linear pair. Angle 1 and 2 are forming that linear pair. It means that these two lines must be perpendicular. So I could say that QV, line segment, or I guess it's a line, QV, is perpendicular to that horizontal line. And by the way, this is the perpendicular statement. I don't know if we've seen that a whole lot yet. QV is perpendicular to PS. Those have to be perpendicular because we've got a linear pair where both angles are congruent. That's what Theorem 3.8 tells us. Now, if we've got these two lines that are perpendicular, we should be able to say that 3 and 4 are complementary. If they're complementary, they form a right angle. The theorem that tells us we can actually say that for sure is another one that we just learned about, and that's Theorem 3.10. 3.10 tells us that if we've got two sides of two adjacent acute angles, and that's really what we've got right here, this side and this side, those are the sides of angles 3 and 4. If we've got those two different sides that are perpendicular, then the angles have to be complementary. Okay, so that's really Theorem 3.10, Theorem 3.10 that gives us justification for that. Theorem 3.10, and that was our proof statement. That's what we were trying to get at, so that's as far as we need to go with this proof. Okay, let's take a look at another one. On the next page, we've got ED and EF that are perpendicular. We're trying to prove that 7 and 8 are complementary, and in one step we could solve this. We could go back to 3.10 again and say that those two angles have to be complementary because the two outside rays of those angles are perpendicular. However, up at the top you might have noticed it says we're proving Theorem 3.10. So this is a proof to show why it's okay for us to use Theorem 3.10 all the time. Okay, so we're going to write down our given. ED and EF are perpendicular. From that point, our next step would probably be to define what we know based on that. DEF, this entire large angle is a right angle. We can use Theorem 3.9 to justify that. Remember, 3.9 says if we've got two lines perpendicular, which we do in that diagram, they intersect to create right angles. Okay, so here's perpendicular lines, they intersect to create that right angle. Now we need to really define what a right angle is. DEF is 90 degrees. That's the definition of a right angle. After that, since we've got two angles that make up that right angle, we could say 7 and 8 have to add up to DEF. That's the angle addition postulate. Small angle plus small angle equals the entire large angle. And now we're going to substitute in. Using the substitution property of equality, here's angle 7, angle 7, angle 8, angle 8. Angle DEF turned into 90 degrees. We just substitute 90 degrees in because we know angle DEF is a right angle. We said that up here, so it's 90 degrees. And then finally, the last step of all of this is to show that 7 and 8 are complementary, and that's really just the definition of complementary angles. If they both add up to 90 degrees, then they both must be complementary. One more proof to test out here. Here's what it looks like. We've got 1 and 2 that are a linear pair, and we know that 1 and 2 are congruent. So we're trying to prove that G and H are perpendicular. This is really a proof of Theorem 3.8. Okay, so let's prove that Theorem 3.8 is correct, and we can use it all the time. The first thing is that we've got a linear pair that's given to us. We know that 1 and 2 are supplementary. Why do they have to be supplementary? Why do they have to add up to 180 degrees? Well, that's because that's what a linear pair is. We call that the linear pair postulate. So you might see that from time to time from this point on. If we've got 1 and 2 that are a linear pair, and we know they're supplementary, what does that mean? We're going to define supplementary. It means that they add up to 180 degrees. So we could say that 1 and 2 have to add to 180 degrees. We didn't have this up at the top. We could have, but now is a good time to bring in that second given where 1 and 2 are the same angle. They're congruent. Because now we can start making use of that. If the 1 and 2 are congruent, then the measures of those angles must be the same. That's just defining what congruent angles are. Right? If they're congruent, they have the same angle measurement. We could have kind of flipped that around as well and started this with this one. If the measures are the same, then we can say they're congruent. That's what defining congruent angles is all about. Now we substitute. In place of here we had angle 1 and angle 2 add up to 180. We've gotten something similar here in step 6. Angle 1 and angle 1 are 180. So we substituted angle 2 out, and in its place we put angle 1. We can do that now that we've stated that those two angle measurements are the same. So that's substitution. Now I'm just going to regroup this. We're going to regroup. I've got measure of angle 1 and measure of angle 1. We're just going to say, well, that's two groups of measure of angle 1. And that's not really a theorem or a postulate. We're just combining like terms in that step. And then finally, the last couple steps bring us down here where we say angle 1 is 90 degrees. I know that's got to be true. Really, all we're doing is going from step 7 and dividing away 2 on each side. That's the division property of equality. If the measure of angle 1 is 90 degrees, now we can say, well, that's what a right angle is. Oh, sorry, in there we should be saying measure of angle 1 is 90 degrees. Don't have the answer listed for you there. And if that's 90 degrees, then that's the definition of perpendicular line. So now we've proven that has to be the case. So a couple different proofs that we've been able to look at now, making use of theorems 3.8, 3.9, 3.10.